There is something in your driveway right now that is slowly being stolen from you. Not by a thief, not by weather, by design. Look at your headlights. If your car is more than 3 years old, there is a good chance those lenses are no longer clear. They are yellow, they are hazy, they scatter light instead of projecting it. And every time you drive at night, your visibility has dropped, in some cases by as much as 79% compared to a new lens. That is not a minor inconvenience. That is the difference between seeing a deer on the road at 200 feet and not seeing it until it is 60 feet away. At highway speed, that gap costs you everything. Now here is the question nobody in the automotive industry wants you to ask. Why does this happen at all? Why does a component that costs the manufacturer less than $11 to produce begin failing within 36 months of purchase? And more importantly, why does every solution sold to you at AutoZone, every kit advertised on late-night television, every service offered at your local detailing shop seem to work for exactly 4 to 6 months before the problem returns? The answer is not technical failure. The answer is architecture. The degradation of your headlights is not a flaw in the system, it is the system. And sitting in a $3 bag at a lapidary supply store, or a jewellery polishing supplier, or an industrial ceramics distributor, is a powder that has been used since the 1940s to polish optical glass with micron-level precision. A powder that costs less than $1 per application. A powder that, when combined with the correct sealing technique, does not just restore your headlights. It permanently resolves the oxidation cycle that the industry has spent 4 decades teaching you to manage instead of eliminate. This is not a life hack. This is not a DIY trick from a Reddit thread. What you're about to learn is the same chemistry used by aerospace engineers to restore polycarbonate canopies on military aircraft. The same abrasive compound used in optical lens manufacturing. It has been hiding in plain sight in industrial supply catalogues, completely outside the vocabulary of the $47 billion automotive detailing industry. Because the moment you understand how it works, you will never purchase another headlight restoration kit again. Stay with this. Before 1987, your headlights could not fog. That is not an exaggeration. It is a materials fact. Every headlight lens manufactured for consumer vehicles before that year was made from borosilicate glass, the same compound used in laboratory equipment and high-heat cookware. Glass does not oxidize. Glass does not yellow. Glass does not develop the microscopic surface crazing that scatters light and turns a precision optical instrument into a frosted window. A 1974 Chevrolet with its original glass headlights, sitting in a field for 20 years, would still throw cleaner light than a 2019 sedan with 3-year-old polycarbonate lenses. That is not nostalgia. That is chemistry. The shift happened at the intersection of 2 industries that had nothing to do with your safety and everything to do with margin. In the mid-1980s, automotive designers began pushing for aerodynamic headlight shapes, curved, integrated, flush with the body panel. Glass could not be molded into those complex geometries at production scale. Polycarbonate could. It was also 50% lighter, virtually shatterproof on impact, and cost significantly less to manufacture at volume. In 1987, the US Federal Motor Vehicle Safety Standards were amended to permit polycarbonate lens housings, and within 8 years, glass headlights had been eliminated from virtually every new passenger vehicle sold in North America and Western Europe. The manufacturers knew what they were accepting. Internal engineering documents from that era, some of which have surfaced through supplier litigation in the late 1990s, acknowledged that polycarbonate had a fundamental vulnerability that glass did not. Ultraviolet radiation breaks the molecular bonds on its surface. Without continuous protection, the degradation cycle begins within 18 to 36 months of first exposure to sunlight. The manufacturer's solution was a factory-applied UV-resistant hardcoat, approximately 2 to 5 microns thick, thin enough to apply cheaply at scale, thin enough to fail within 3 years of normal use, and once that coating is gone, the bare polycarbonate underneath degrades at an accelerating rate, because now the UV radiation is hitting an unprotected surface that was never designed to be exposed. This was documented, this was known, and no manufacturer has ever moved back to glass, because the replacement cycle that polycarbonate created is not a problem for them. A new OEM headlight assembly for a 2018 Honda Accord costs between $280 and $420 per side. A full replacement on a luxury vehicle can exceed $1,900 for a single unit. The degradation that begins the moment your factory UV coat wears through is not a warranty issue, because by the time it becomes visible, the vehicle is almost certainly outside its headlight coverage window. The timeline was engineered. The obsolescence was scheduled. What makes this particularly precise as a form of institutional deception is how seamlessly the restoration industry rose to fill the gap. Within years of polycarbonate becoming universal, a market appeared: kits, compounds, services, all of them designed around the same fundamental limitation. They address the surface. They sand away the top layer of oxidized material. They make the lens clear again, but none of them, not a single commercially marketed product in the mainstream detailing industry, applies a UV barrier with sufficient optical clarity and bond strength to actually stop the cycle from restarting. They restore. They do not resolve, and they were never meant to. The powder that breaks this cycle was not developed for headlights. It was not developed for cars at all. Cerium oxide is a rare earth compound, atomic number 58 on the periodic table, a byproduct of lanthanide processing, and one of the most precisely abrasive substances known to materials science. Its hardness on the Mohs scale sits at approximately 6, which places it above most surface contaminants and oxidized polymer layers, but below the base polycarbonate you are trying to preserve. That gap is not accidental. It is the entire mechanism. Cerium oxide does not scratch what you're trying to save. It removes only what has already been destroyed. Here is what is actually happening to your headlight at the molecular level. Polycarbonate is a thermoplastic polymer, a long chain of carbonate-linked bisphenol A units that gives the material its clarity and impact resistance. When ultraviolet radiation, specifically UVB wavelengths between 280 and 315 nanometers, strikes an unprotected polycarbonate surface, it breaks the ester bonds in those polymer chains in a process called photooxidation. The broken chains react with atmospheric oxygen and water vapor. The result is a layer of degraded polymer, yellowed, brittle, optically diffuse, that sits on top of the still intact polycarbonate beneath. That layer is typically between 100 and 400 microns deep in a heavily oxidized lens. It looks like the entire headlight has gone bad. In most cases, 90% of the lens beneath that layer is structurally and optically sound. This is where cerium oxide performs a function that no commercially marketed headlight restoration compound replicates with the same precision. When cerium oxide particles, typically between 0.5 and 5 microns in diameter, are suspended in water and applied with mechanical agitation, they do not simply abrade the surface the way sandpaper does. They engage in what materials scientists call a chemical-mechanical polishing action. The cerium ions form temporary chemical bonds with the oxidized polymer surface, weakening the degraded layer at the molecular level, while simultaneously polishing it away with mechanical friction. The result is not just a smoother surface. It is a chemically cleaner one, with the oxidized material removed at a depth and consistency that purely abrasive compounds cannot achieve. This is the same process used by semiconductor manufacturers to polish silicon wafers to sub-nanometer flatness. It is the same compound used by opticians to polish high-index glass lenses. The US Air Force has used cerium oxide-based compounds in field restoration protocols for F-16 canopies, polycarbonate panels that must maintain optical clarity under conditions far more extreme than a parking lot in Phoenix. The chemistry is not obscure. It is well documented in material science literature going back to a 1950 paper by Cook and Bates published in the Journal of the American Ceramic Society. It simply never made it into the vocabulary of the consumer automotive market, and it is worth pausing here to ask why. Now, an honest assessment before continuing. Cerium oxide is not a universal solution, and presenting it as one would be the same category of deception being exposed here. If the oxidation on your lens has penetrated deeper than 400 microns, which can happen on vehicles in high UV environments that have been neglected for more than 5 to 7 years, the chemical-mechanical action of cerium oxide will reveal haze that exists below the layer it removes. In those cases, a preliminary wet sanding sequence with 800 to 1,500 grit automotive sandpaper is necessary before cerium oxide is applied. The powder restores what can be restored. It does not fabricate clarity where the substrate itself has been compromised. That distinction matters, and ignoring it is how people end up with worse results than they started with. But for the vast majority of oxidized headlights, the hundreds of millions of lenses currently on vehicles across North America alone, the degradation is entirely within the reach of this compound. The oxidized layer is there, the intact polycarbonate is beneath it, and a $3 bag of cerium oxide powder contains enough material for 8 to 12 full headlight restorations. What happens after the restoration is where the industry's deepest deception lives. The number that needs to be said out loud is $47 billion. That is the current valuation of the global automotive detailing and appearance products market as of 2024, according to Grandview Research. Not the entire auto industry, not parts and service. Just the segment dedicated to making your car look the way it should have looked when you bought it. And sitting inside that $47 billion ecosystem, occupying one of its most reliably recurring revenue streams, is the headlight restoration category, a market that by conservative industry estimates generates over $2 billion annually in product sales, professional services, and replacement lens assemblies across North America alone. Understand the architecture of that number. Every dollar in that $2 billion exists because the restoration does not last. A detailing shop charges between $35 and $90 to restore a pair of headlights using compounds that cost them less than $4 in materials. The service needs to be repeated every 6 to 18 months. A customer who owns a vehicle for 10 years and visits that shop twice a year spent between $700 and $1,800 on a problem that $6 in cerium oxide and a $12 can of UV-resistant clear coat would have permanently resolved after the first treatment. That is not a calculation the detailing industry publishes. That is a calculation they are structurally incentivized to prevent you from ever making. The product side of this equation is no less precise in its design. The headlight restoration kit market, brands like Meguiar's, 3M, Turtle Wax, Sylvania, generates an estimated $400 million per year in retail sales in the United States alone. The average kit retails between $18 and $35 and contains a graduated sandpaper sequence, a polishing compound, and a small bottle of UV sealant. That sealant is the mechanism of the recurring revenue. It is applied by hand, bonds weakly to the freshly polished polycarbonate, and begins degrading within 4 to 8 months. The manufacturers know this. The performance window is printed in the fine print of the instructions as a feature. Reapply every 6 months for best results, rather than identified as the fundamental inadequacy it represents. The $47 billion market does not sell you solutions. It sells you subscriptions to the illusion of solutions. Now place the automotive OEM layer on top of this. The 10 largest automobile manufacturers in the world, Toyota, Volkswagen, Stellantis, Ford, GM, Honda, Hyundai, Kia, Mercedes-Benz, BMW, and Nissan, collectively sell replacement headlight assemblies as one of the highest margin components in their parts catalogues. A headlight assembly that costs $11 to $18 in raw materials to manufacture carries an OEM retail price between $180 and $1,900, depending on vehicle make and model. The degradation cycle that polycarbonate creates does not just feed the detailing market. It feeds the replacement parts market. It feeds the insurance claims market, where foggy headlights contribute to nighttime accident rates that the National Highway Traffic Safety Administration estimated in 2019 cost the US economy $242 billion annually. Every layer of this industry is downstream of the same original decision, to use a material that degrades instead of one that does not. This is the moment in this video where you either accept that what you are watching is a pattern, or you dismiss it as coincidence. The $47 billion market did not cause the switch to polycarbonate, but it grew in the shape of that switch, perfectly, the way a vine grows in the shape of a fence. The restoration industry needed the degradation to exist. The product manufacturers needed the restoration to be temporary. The OEMs needed the assemblies to be replaceable. And the compound that interrupts all 3 of those revenue streams costs less than $1 per use and has been sitting in industrial supply catalogues since before most of the cars on the road today were built. You are not a customer in this system. You were designed to be one. Cerium oxide powder. That is the full name of what you are looking for, not a kit. not a branded compound. The raw industrial powder, sold under the category of lapidary supplies, optical polishing agents, or glass polishing compounds. On Amazon, it is available in 4-ounce bags for between $8 and $12, which contains enough material for 10 to 15 full restorations. From industrial suppliers like Kingsley North or African Import, the price drops to approximately $3 to $4 per 100 grams. 100 grams is more cerium oxide than most people will use on their own vehicles in a decade. You will also need a variable speed drill or rotary tool, a foam polishing pad that attaches to it, the kind sold for $4 to $6 at any hardware store, a spray bottle filled with clean water, painter's tape, microfiber cloths, and a can of automotive UV-resistant clear coat. Total investment for a first-time setup is between $18 and $28. A single professional restoration service at a detailing shop costs between $35 and $90 and lasts 6 months. The math requires no further commentary. Before touching the lens, tape off every surface surrounding it: the paint, the trim, the rubber seals. Cerium oxide in slurry form will not damage those surfaces catastrophically, but it will work into gaps and leave residue that is difficult to remove from textured plastic. Take 4 minutes to tape. It matters. Then assess the lens under direct light. Run your hand across the surface. If you feel deep pitting, craters you can catch your fingernail in, you need to begin with wet sanding before the cerium oxide phase. Use 800 grit wet-dry sandpaper, kept continuously wet, in straight horizontal strokes across the full face of the lens. Apply moderate pressure, not aggressive force. You're not trying to remove material rapidly. You're leveling the surface so the cerium oxide has a consistent plane to work from. Follow the 800 grit with 1000, then 1500, then 2000, each pass reducing the scratch pattern left by the previous one. After the final sanding pass, the lens will look worse than when you started. Uniformly hazy, flat, completely opaque. This is correct. This is the process working. If the lens shows only yellowing and light surface oxidation with no deep pitting, skip the sanding entirely and begin directly with the cerium oxide phase. Mix the powder with clean water in a small container. The consistency you're targeting is slightly thicker than whole milk, thin enough to flow but with enough suspension to coat the pad evenly. There is no precise ratio because cerium oxide slurry is forgiving within a wide range. A working approximation is 1 teaspoon of powder to 2 teaspoons of water, adjusted by eye. Load the foam pad, attach it to your drill, and set the speed to between 1,200 and 1,800 revolutions per minute. Lower than that, and you lose the mechanical component of the chemical-mechanical action. Higher than that on a dry pass, and you risk generating enough heat to warp the lens surface. Keep the lens wet throughout the entire process. Spray water directly onto the lens every 30 to 45 seconds. The slurry should never dry on the surface while the pad is moving. Work in overlapping circular passes across the entire lens face, maintaining consistent pressure and keeping the pad flat against the surface. You will see the slurry turn from white to a faint yellow-grey as it lifts oxidized material. This is the process working at the level it is supposed to work. Continue for 3 to 5 minutes of active polishing per lens, adding water as needed. Wipe the lens clean with a microfiber cloth and assess. In most cases of moderate oxidation, a single pass is sufficient to restore full optical clarity. For severe cases, repeat the process once more before moving to the sealing phase. Do not skip the sealing phase. This is where every commercial kit fails you, and where this method permanently diverges from the restoration cycle the industry depends on. The sealing step is the entire difference between a restoration that lasts 4 months and one that lasts 4 years. What you're applying is not a wipe-on UV sealant from a kit bottle. You're applying automotive-grade UV-resistant clear coat, the same category of product used to protect painted exterior surfaces from the same UV degradation that destroys polycarbonate. Brands like Rust-Oleum 2X, Spraymax 2K, or Duplicolor Clear Coat are available at any auto parts store for between $8 and $18 per can. Of these, Spraymax 2K is the most chemically durable option. It is a 2-component isocyanate clear coat that cross-links as it cures, forming a bond with the polycarbonate surface that is categorically harder and more UV-resistant than any sealant included in a retail restoration kit. It retails for approximately $18 to $22 per can and will seal 6 to 8 headlight pairs per can. Apply the clear coat in 2 thin passes, allowing 5 minutes between coats. Hold the can 8 to 10 inches from the lens surface and use smooth, even strokes that extend past the edge of the lens on each pass. Do not attempt to achieve full coverage in a single heavy coat. Solvent trap and runs are the result of impatience here, not technique. After the second coat, allow the lens to cure undisturbed for a minimum of 4 hours before exposing it to moisture, and 24 hours before any contact. The Spraymax 2K continues cross-linking for up to 72 hours after application, reaching its maximum hardness and UV resistance at that point. What you have applied at that stage is not a temporary sealant. It is a new hard coat, functionally equivalent to the factory UV coating the manufacturer applied at production, and in the case of Spraymax 2K, chemically superior to it in terms of bond strength and UV inhibitor concentration. The total time investment for a pair of moderately oxidized headlights using this method is between 45 minutes and 90 minutes. The cost per restoration after the initial tool setup is under $3. The expected service life of the result, based on the UV resistance ratings of 2-component automotive clear coats under standard environmental testing, is 4 to 6 years, with the option to apply a single maintenance coat at that point rather than repeating the full restoration. This is what a permanent solution looks like, and the reason it has never appeared in a mainstream automotive publication, never been featured in a manufacturer's care guide, never been recommended by a dealership service department, is the same reason you had to find it here. There is a version of this video that does not exist, the one where every oxidized headlight on every car responds perfectly to cerium oxide and a rattle can of clear coat, where the process works identically regardless of lens condition, vehicle age, or geographic history. That version would be a different kind of deception, and it has no place here. The method described in this video has boundaries, and understanding those boundaries is what separates someone who gets a permanent result from someone who spends 90 minutes and ends up with a lens that looks marginally better than when they started. The first boundary is depth of oxidation. Cerium oxide removes material at the surface level. Its chemical-mechanical action is precise, but it is not unlimited in depth. On a lens where UV degradation has penetrated beyond approximately 400 microns into the polycarbonate substrate, the cerium oxide process will clear the upper oxidized layer and reveal a secondary haze underneath that no amount of continued polishing will resolve. This condition is most common on vehicles that have spent 5 or more years in high UV environments, the American Southwest, coastal Florida, high-altitude regions, without any restoration or protection applied during that period. If you polish a lens to clarity, and the haze returns within minutes of wiping it clean, you are looking at subsurface degradation. The lens is telling you something the powder cannot fix. The second boundary is structural. Polycarbonate that has been oxidized beyond a certain threshold becomes physically brittle at the surface level. The polymer chains have been broken so extensively that the material no longer has the integrity to hold a polished finish or bond reliably with a clear coat. You can identify this condition before you begin by pressing firmly on the lens surface with your thumb. A lens with compromised structural integrity will show a faint white stress pattern under that pressure, visible as a momentary cloudiness that disappears when you release. If that stress pattern appears, the substrate has been damaged past the point where surface restoration is viable. Continuing with the process will produce a result that degrades within weeks rather than years, because you are sealing a surface that is actively continuing to break down beneath the coating. The third boundary is prior treatment. If a previous restoration used a silicone-based sealant, which includes the majority of wipe-on UV protectants sold in retail kits, that silicone layer must be fully removed before cerium oxide can make proper contact with the polycarbonate. Silicone does not sand away cleanly and resist chemical stripping. The indicator is a lens that feels slightly tacky or has an uneven sheen in raking light. In this case, a thorough wipe down with isopropyl alcohol at 90% concentration or higher, followed by a light 2000 grit wet sand, is necessary to clear the contamination before the cerium oxide phase begins. Skipping this step results in uneven polishing and poor clear coat adhesion, the two failure modes that make a restoration look worse at 60 days than it did at completion. These are not edge cases. On any given parking lot, a meaningful percentage of vehicles with visibly oxidized headlights will fall into one of these 3 categories. Knowing which category you are dealing with before you begin is the difference between an hour of productive work and an hour of compounding a problem. Assess the lens in direct sunlight before you tape anything off. Look for the stress pattern under thumb pressure. Look for subsurface haze that persists after a preliminary wipe. Feel for the tacky silicone residue. If none of those conditions are present, the method works. If one of them is present, you now know exactly what to do about it, or exactly when to accept that the lens has passed the threshold where restoration is the right answer and replacement is the honest one. A replacement polycarbonate lens from an aftermarket supplier, not OEM, not dealership, costs between $18 and $65 for most common vehicle makes and models. That number exists because the same industry that charges $280 to $420 for an OEM assembly also created a secondary market it cannot fully control. The knowledge of where that market is and how to use it is the same category of information as everything else in this video. You came to this video because something was wrong and nobody in the system designed to help you was actually helping you. The dealership quoted you a number, the detailing shop gave you a result that lasted 4 months. The kit from the auto parts store is sitting in your garage with one application left in the sealant bottle and a lens that is already starting to haze again. You did not end up here by accident. You ended up here because you stopped accepting the cycle as inevitable. That shift, from consumer to someone who understands the architecture of what is being sold to them, is not a small thing. It is the only thing that actually changes your relationship with every industry that profits from your dependency. The $47 billion detailing market does not fear the person who buys a different brand of restoration kit. It has no defense against the person who stops needing the category entirely. 1 bag of Cerium oxide and 1 can of Spraymax 2K removes you from that revenue stream permanently. Not for this year. Permanently. And when you do this in your driveway and your neighbour asks what you used, and you tell them you have just removed 2 customers from a market that depends on neither of you ever having this conversation. This channel exists because that conversation keeps getting buried. Not dramatically. No documents get shredded. No whistleblowers disappear. It gets buried the way all inconvenient knowledge gets buried in the modern information environment, by being absent from the places people think to look, by being outside the vocabulary of the publications and platforms that the industry funds through advertising, by never appearing in the owner's manual or the service department recommendation, or the sponsored content that fills the top of every search result on the topic. The knowledge is not hidden. It is just never where you're looking when you need it. Every person who shares this video is not supporting a channel. They are placing this information one step closer to someone who is about to spend $80 on a kit that will fail in 6 months, or $400 at a dealership service counter, or $1,900 on a replacement assembly that a $3 powder and 20 minutes of their time would have made unnecessary. That is what sharing means in this context. It is not engagement, it is intervention. If this video reached you before that expense, share it with one person it might reach before theirs. Not as a recommendation. As a correction to a system that has been charging both of you for a problem it knows how to prevent and has chosen not to. Subscribe not because this channel needs the number, but because the next video in this series goes further into the $31 billion automotive glass treatment market and the single compound that the 3 largest windshield coating manufacturers have spent 15 years making sure you have never heard of.